Have you ever stopped to watch a tiny stream of ants marching across your kitchen counter or a sun-drenched sidewalk? They move with an unnerving purpose, a collective focus that seems almost intelligent. You might see a scout suddenly break away. Then a few minutes later, an entire column shifts direction, or even a sudden panic erupts. What just happened? Did they text each other? Did a general issue an order? For centuries, we've looked at these six-legged automatons and seen only instinct. But what if I told you that beneath your feet every day, a complex silent language is being spoken? A language of chemicals, vibrations, and touch that coordinates millions of individuals into a single terrifyingly efficient entity, a superorganism. The truth is, ants have evolved one of the most brilliant communication systems on Earth, using a molecular dialect that rivals any human language in its complexity and immediate impact. We're not talking about simple follow the leader. We're talking about an intricate blend of 4 distinct modes of messaging: chemical, tactile, acoustic, and even visual. This isn't just about finding sugar. It's about life, death, war, and the cohesion of a colossal society. Prepare to have your mind blown. We're diving deep to decode the secret messages of the ant world. From the invisible evaporating chemical trail that leads to your discarded picnic to the terrifying sound that signals a colony-wide panic, this is how ants communicate, and what their microscopic conversations reveal about the nature of intelligence. The cornerstone of all ant communication, the very airwaves of their society, is chemistry, specifically through unique chemicals called pheromones. Think of pheromones not as a general smell, but as a highly specific, instantly understandable word or phrase. The myth we often hold is that ants just smell the food and go to it. The reality is far more sophisticated. When a scout ant finds a glorious jackpot, say a drop of spilt soda, it doesn't just wander back. It lays a trail pheromone from a gland in its abdomen on the return journey. This trail is a masterclass in chemical precision. It's sticky enough to hold the message, but volatile enough to evaporate. Why is evaporation important? Because it acts as a self-erasing map. If the food source is temporary, the trail, the message, fades, preventing the entire colony from wasting time on a dead end. This is a brilliant, self-regulating system that maintains the colony's foraging efficiency. Now here's the surprising fact. The more ants that successfully follow the trail and return with food, the more they reinforce the chemical message. It's like a viral social media post. Low concentration is a whisper. High concentration, reinforced by hundreds of workers, is a shout. The connection is that this is essentially a decentralized decision-making process. No general is giving the order. The collective action of successful foragers is dynamically drawing the resource map for the entire colony. This chemical language is responsible for the colony's very existence, defining their foraging routes, managing their workforce, and coordinating their lives. But what happens when the message isn't about dinner, but about an existential threat? We need to look at another, more volatile type of pheromone that triggers an immediate, colony-wide panic. When we encounter danger, we might yell or call 911. When an ant encounters a threat, a predator, a broken tunnel, or a human thumb, it deploys a different set of chemicals, the alarm pheromones. The common myth is that all ants respond to danger in the same aggressive way. But the reality is that the response is far more nuanced, even species-dependent. For small, less popular species, a low concentration of alarm pheromone triggers a panic response. Not a fight, but an immediate mass evacuation. They scatter, or even grab their larvae and flee to a safer chamber, prioritizing the survival of the offspring over a futile defense. Now, for the surprising fact, the concentration of the alarm pheromone often dictates the exact behavior. A low concentration might incite cautious investigation. Something is wrong. Go check it out. A high, overwhelming concentration, often released by an ant that is physically crushed or severely injured, signals catastrophe, triggering the mass flee or freeze response. Imagine a gas leak in a building, but the gas itself tells you the precise level of danger. The immediate connection here is the brilliance of the chemical cascade. Different chemical compounds, sometimes released from the same gland, act as distinct words in their alarm vocabulary. Some trigger aggression, others flight, and some even coordinate an organized defense depending on the need. It's a chemical mobilization unit, all sensed by the specialized receptors on their antenna. This level of immediate nonverbal coordination is why even a small colony of fire ants can mobilize a swarm attack in seconds. The next time you disturb an ant nest, watch closely. If they scatter instantly, you're witnessing a perfectly executed chemical panic response. But alarm isn't the only time they communicate about identity. They also have a sophisticated system for figuring out, are you one of us? In an ant colony that can contain hundreds of thousands or even millions of members, how do they tell friend from foe? The myth is that they simply recognize each other visually. The truth is that ant society is built on a literal shared scent, the colony odor, made up of chemicals called cuticular hydrocarbons, CHCs, that coat every ant's exoskeleton. CHCs are waxy molecules that serve as a waterproof barrier, but more importantly, they are the colony's ID card and passport, all in one. The surprising fact is that the colony odor is not genetic. It's acquired and maintained. It's a chemical cocktail mixed from the queen's specific pheromones, the food they eat, and even the materials of the nest. To ensure every ant carries the correct up-to-date signature, they constantly groom and feed each other, a process called trophallaxis, which we will explore later. The connection is profound. An ant from an alien colony, if it could somehow be coated with the CHCs of another nest, might be accepted, at least temporarily. Conversely, a native ant, if it's been away too long or is covered in the wrong chemicals, risks being recognized as an intruder and attacked instantly. This chemical ID system is so refined that it can even signal an ant's role, age, or fertility status within the nest. The CHCs are their version of a social security number and a uniform combined. It's a chemical security system where the smell of the colony is literally the social contract. But communication isn't only about chemicals. Sometimes the message requires direct physical contact. While chemical signals can travel long distances, they can also be too general or too slow for urgent. One-on-one information exchange in the dark, crowded tunnels of the nest. This is where tactile communication, the language of touch, comes in primarily through the antennae. The myth is that ants only use their antennae to smell. The reality is they are hypersensitive, multifunctional organs covered in thousands of tiny sensory hairs called sensilla that detect chemical, physical, and even thermal cues. When two ants meet, they engage in a rapid, complex exchange called antennal drumming, or antennation. This is their handshake, where they quickly tap each other's bodies to exchange CHCs, confirming identity, and pass on specific high-priority information. The surprising fact is a behavior known as tandem running, observed in certain species. A knowledgeable ant leads a less informed nestmate to a new food source or a new nest site. The follower ant maintains constant tactile contact, tapping the leader's abdomen with its antennae. If the follower loses contact, the leader literally stops and waits. This is one of the clearest examples of what scientists call teaching in non-human animals, where the teacher modifies its behavior to facilitate learning in the student. The connection. Touch is vital not just for ID, but for real-time navigation and the one-on-one transfer of critical localized spatial data. It's the ultimate GPS and knowledge transfer system. This tactile conversation is a constant hum in the colony, regulating traffic and ensuring social cohesion. But there is a time when a simple tap isn't enough, and a louder, more immediate signal is required. Ants are largely silent to human ears, which perpetuates the myth that they do not use sound. But the surprising truth is that many ant species use acoustic communication, often through a process called stridulation. Stridulation is produced by rapidly rubbing two specialized body parts together, like the scraper on one segment of the abdomen against a file on another. It's like a tiny built-in cricket that transmits a vibration directly into the substrate of the nest. The surprising fact is the utility of this silent sound. For a trapped ant, perhaps one caught in a cave-in or pinned by a predator, stridulation acts as a distress call. The vibrations travel through the earth and the nest walls, alerting nearby nestmates to the exact location of the trapped individual, prompting a rescue attempt. Furthermore, in massive-scale projects like those undertaken by leafcutter ants, specific stridulations are used to coordinate workers. A worker might vibrate a leaf, its cutting to signal to others the leaf's suitability, or to mark a spot for reinforcement during tunnel construction. The connection. This is a highly localized emergency communication system that bypasses the need for the slower diffusion of chemical signals. It's their immediate help button, often too faint for us to hear, but absolutely vital for survival in the dark, dense environment of the colony. Ant communication is a multi-layered masterpiece. They speak through the air, the ground, and direct contact. But a particularly fascinating conversation revolves around the queen. The queen is often perceived as the ruler of the colony, actively giving commands. The myth is that she dictates by physical force or superior size. The biological reality is that her authority is chemical. The queen ant uses specialized queen pheromones to maintain the social order and, critically, to regulate the fertility of her worker daughters. The surprising fact is that in many species, the worker ants are genetically capable of reproduction, but the presence of the queen's pheromone actively suppresses their ovaries. It's a chemical message broadcast throughout the nest that says, "I am the reproductive powerhouse. No one else needs to lay eggs." This ensures that the workers remain sterile and focused solely on foraging, defense, and care of the young. This pheromone is constantly circulated throughout the colony via trophallaxis, mouth-to-mouth food sharing. The connection. This makes the queen pheromone a master control signal. If the queen dies or is removed, this pheromone fades. The suppression lifts, and some workers may begin laying their own eggs, leading to chaos, or the colony will immediately begin rearing new queens to replace the fallen leader. The queen doesn't rule. She simply is the chemical status quo. This chemical control is the engine of ant society, keeping the hierarchy rigid and efficient. But their conversation doesn't end at the borders of the colony. They also have to communicate about outsiders. The ant world is a constant battlefield, and their communication systems are often repurposed for chemical warfare or deception. The myth is that ant-on-ant interactions are just about raw physical aggression. The reality is that chemical signaling is their primary weapon. The surprising fact is the existence of specialized chemicals designed to confuse, disorient, or even lure rival species. Some ants are known to release pheromones that mimic the alarm signals of a different species, effectively causing a false panic in the rival colony. This is chemical espionage. Others use powerful chemicals, often components of their venom like formic acid, not just to sting but to act as a potent, toxic alarm pheromone to the target species. The connection is a dark biological twist. An ant can use a signal, a word, meant for one context, alarm, and deploy it to devastating effect in another, warfare, exploiting the universal language of fear in the insect world. It's a literal chemical fog of war, where the enemy is blinded and confused by tailored molecular messages. Their communication is brilliant, but it's fundamentally different from ours. We must recognize that difference to truly appreciate their genius. To truly grasp ant communication, we must discard the final human-centric myth that ants talk with intent like we do. The reality, as noted by leading entomologists, is that ant communication is primarily modulatory, not fully referential. In human referential communication, you consciously decide to send a specific message to mean a specific thing. The food is 30 feet to the right. The listener then processes that intent. The surprising fact is that for ants, the signal often works differently. The pheromone doesn't say go to the food. It says increase your probability of walking in this direction or increase your probability of aggression. The chemical signal doesn't encode a complex set of coordinates. It simply modulates the receiving ant's behavior, turning a general tendency into a high-probability action. The connection. The collective intelligence of the colony emerges from these simple probability-changing messages. Millions of simple, non-intentional signals combine to create a perfectly optimized, resource-gathering or self-defending superorganism. The ants don't need language in the human sense because their success lies in a decentralized automatic response to chemical triggers. They are a network, and the signal is the simple data packet that makes the network hum. It's an evolutionary shortcut. They don't need the cognitive overhead of a brain to process language. They just need the antennae to read the instruction manual coded in a scent. The next time you see a line of ants, remember this. You are witnessing a chemical opera, a performance of complex, nonverbal genius that has allowed these tiny creatures to dominate ecosystems across the globe. If you've learned something truly amazing today about this incredible superorganism, don't let the curiosity stop here. Smash that subscribe button and ring the bell so you never miss another deep dive into the fascinating world of facts, science and history. Now for a question. Which of these communication methods, the self-erasing pheromone trail, the chemical ID card, or the silent distress call, did you find the most mind-blowing? Let us know in the comments below. Your answers help us decide which secrets of the universe we should unlock next. We started by asking how ants communicate, and what we found is a multifaceted, elegant system that defines their very existence. They communicate primarily via pheromones, the chemical language of survival, laying down dynamic trails for food and volatile alarms for danger. They use tactile communication, the antennal drumming and food sharing that maintains the colony odor and transfers real-time information. They employ acoustic signals like stridulation to call for help when trapped. Their genius lies not in spoken word, but in efficiency. Every worker is a mobile chemical sensor, instantly reading the molecular mood of the colony. The ant superorganism is a marvel of decentralized control, held together by an invisible lexicon of scent. The world is full of these silent conversations. All you have to do is stop, look closer, and remember the impact phrase of today's journey, that the complexity of the microscopic world often far surpasses the grand gestures of our own. What other secret languages are being spoken right under our noses? Keep questioning and we'll keep exploring.